talking about data transformation. Data transformation is the process of converting data from one format or structure to another. It's performed to meet the requirements of statistical and data mining techniques used for the analysis. What are the examples of data transformation? Sometimes we transform numerical data, including transforming an individual's date of birth to age. So we have date of birth given to us. We don't want it. We want to convert it to age. Combining height and weight to create a new variable, let's say the body mass index. Sometimes you don't need the height and weight. You want to create mathematical conversion, mathematical equation to create a new variable called the body mass index. Or sometimes you create percentages or converting values to natural logarithmic or natural logarithms, and this is very common. Sometimes it makes sense to group a vast range of numerical values into a small number of bins. For example, we might want to arrange numerical ages into age intervals or age groups. You have ages of thousands of people you would like to create groups, or you have income. You have income and you'd like to create income groups, or you have seasons, fall, winter, spring, summer, and you'd like to have them into, or the opposite way around. You have dates and you want to convert them to seasons, or you have days, you want to convert them to weekdays and weekends. So in this lesson, we will be talking about transforming numerical variables and categorical values and mathematical transformation of numerical variables. So the first technique we will be talking about is binning. Binning is the process of transforming numerical variables into categorical variables by grouping the numerical values into a small number of groups or bins. It's important that the bins are consecutive and non-overlapping so that each numerical value falls into one and only one bin. For example, you might want to transform income values into 3 groups: below $50,000, between $50,000 and $100,000, and above $100,000. The 3 income groups can be labeled as low, medium, and high, or by numbers 1, 2, and 3. Binning can be an effective way to reduce noise in the data. If you believe that all observations in the same bin tend to behave the same way, so you can group them. I mean, it's a good idea to group and create binning for your data sometimes. For instance, the transformation of the income values into 3 groups makes sense when we are more interested in a person's earning power. Does he make a low income or medium or high rather than actual income value? An important advantage of binning is that it reduces the noise in the data, often due to minor observation errors. For example, with binning, outliers in the data, individuals with extremely high income, perhaps recorded incorrectly, will be part of the last bin and therefore will not distort subsequent data analysis. You have outliers. So when you have outliers, when you put them in groups, then you are basically distort or eliminate that noise. So binning is also useful in categorizing observations and meeting the categorical data requirements of some data mining analytics techniques, especially in naive Bayes. In addition to binning numerical values according to user-defined boundaries, bins are also often created to have equal intervals. So we have to create equal intervals. For example, we can create bins that represent an interval of 10 degrees in temperature or 10 years in age. We can also create bins of equal counts, where individual bins have the same number of observations. For instance, by binning a class of 200 students into 10 equal size groups based on their grades, we can find out the relative academic standing for the students. Students in the bin with the highest grades represent the top 10% of the class, so you can create equal intervals or user-defined intervals, not equal intervals, but the best way to use binning is actually create equal intervals. Another type of transformation is mathematical transformation. We talked about binning, which is kind of a grouping. Now we will be talking about something else. Data transformation is an important step in bringing out the information in the data set, which can then be used for further data analysis, in addition to binning, as we said. Another common approach, which is mathematical transformation of existing variables. As we said, if you have height and weight, we don't want height and weight. We want to calculate the body mass index. by dividing the weight by the square root, by the square root of the height in meters, etc., because we want to focus on the body mass index. Then we can calculate the trend and or analyze the trend, or we can transform some values to percentages because it gives you more information. Sometimes the data on variables such as income, firm size, and house prices are highly skewed. So the extremely high values or low values of skewed variables significantly inflate or deflate the average for the entire data set, making it difficult to detect meaningful relationship with the skewed variables. A popular mathematical transformation in this case to reduce the skewness is using the logarithmic transformation. So to kind of reduce the skewness, we use the logarithmic, and we are going to see this in chapter 8 or 7 or 8 or something like this. Another common data transformation involved calendar dates. Because in R, OR usually stores date as numbers. So in R, objects are stored as the number of days since January 1970, using negative numbers for earlier dates. So we have to be careful here. So a transformation of the date values is often performed to help bring useful information out of the data. For instance, a retail company might convert customers' birthdays into ages. We talked about this. We need the ages, not the birth date. Sometimes transforming data or date values into seasons help enrich the data set by creating relevant variables to support subsequent analysis. By extracting and focusing on the months in which gym members first joined the health club, we may find that members who joined during the summer months are more interested in the specific type of exercise programs, whereas people who joined in the winter months are more interested in another type of exercises or programs. So that's why we do some kind of transformation of the data. Finally, another common transformation for the numerical data is rescaling. Rescaling performed when the variables in a data set are measured using different scales, and this is very important, and we are going to address this in chapter 11 when we do something called normalization and standardization. For example, annual income measured in dollars, typically they range from thousands to millions, but number of children in a single family is low, between, let's say, 1 to 10, right? So the variability in measurement scales can have an influence on the larger scale variables. As a result, give you an inaccurate outcomes. So how to deal with this? We do something called standardization or normalization, and it's part of the data mining techniques. And this will be discussed, as I said, in chapter 11 or 12. Okay, now let's talk about how to transform categorical data. We use labels or names to identify the distinguishing characteristics of a categorical variable. For instance, a company may identify each customer as either a male or a female. Here, the sex of a customer is a categorical variable representing two values, two categories. Categorical variables can also be defined by more than two categories. Examples of this: the marital status, single, married, widow, divorce, etc., and the performance of the manager, excellent, good, fair, poor. And as we said in chapter 1, we use nominal and ordinal measurement scales to represent categorical variables. The measurement scales for marital status and performance of the manager are nominal and ordinal respectively. So the marital status is nominal, but the performance of manager is ordinal. While the categorical variables are known to represent less sophisticated levels of measurements, they are often the most important variables in the analysis. For instance, the sex of the customer may contain the most useful information on the customer's spending behavior. Maybe people in general believe that female spends more male, right? So categorical data do, however, present unique challenges in data analysis, and this is important, and they have many challenges to analyze categorical data. As many analysis techniques are limited in their abilities to handle categorical data directly so what we do, we simplify or transform categorical data into numerical formats. We have categorical data So we have a limited techniques to analyze them. So what we do, we transform them into numerical formats before starting doing the analysis. And now we will be focusing in this chapter, we are going to focus in the 3 common approaches of transforming categorical data. Number 1, something called category reduction. Number 2 is dummy variables. Number 3 is category scores. And these are important, by the way. Category reduction. Sometimes nominal or ordinal variables come with too many categories. So this represents a number of potential problems. First, variables with too many categories make the analytical model overly complex because unlike a single parameter of a numerical variable, several parameters associated with the categories of a categorical variable must be analyzed. The second problem is what? If the variable has some categories that rarely occur, it's difficult to capture the impact of these categories accurately. Also, a relatively small sample may not contain any observation in certain categories, creating errors. This will create errors. Finally, if one category clearly dominates in terms of occurrence, and we will see this a lot, the categorical variable will fail to make a positive impact because modeling process is dependent on being able to differentiate among the observations. And as I said, this will be seen a lot. So in this case, what we have to do, we have to use something called category reduction. So the effective strategy to deal with such issues is category reduction. What we do, we collapse some of the categories to create fewer non-overlapping categories. How to determine the appropriate number of categories? It depends on the context, on your data, the norms. The first guideline we may suggest is that categories with a few variables, with a few observations, very few observations, may be combined together into another group called others. For example, in a data set that contains demographic data about potential customers, if many zip code categories only have a few observations, it's recommended that another category called other to be created. Why is that? Because the other category help reveal patterns and relationships in the data. Another guideline to reduce the categories, that categories with a similar impact may be combined. Example, when studying public transformation, one tends to find that ridership levels remain relatively stable during the weekdays. So maybe, and then it change, or let's say it changes a lot in the weekend. So in this case, what you do, you gather the weekdays into one categories under a category called weekdays, and you put Sunday and Saturday together into another category called weekends. So you had 7 categories, now you have 2 categories. The other technique of transforming categorical variable is using dummy variables. In many models, especially in regression models, categorical variables must first be converted into numerical variables. We can't use categorical variables in our regression model, so we have to change the categorical variables into numerical numbers. And for other models, dealing with numerical data is easier than categorical data because it avoids complexities. So the dummy variable, what is the dummy variable? The dummy variable is an indicator or a binary variable. It's commonly used to describe 2 categories of a variable. It assumes a value of 1 for one of the categories and 0 for the other category. So this variable that we add takes only 2 values, zeros and ones. Referred to the other category, which is the 0 category, we refer it as the reference or the benchmark category. For example, we can define dummy variable to categorize a person's sex using 1 for male and 0 for female. So using females as the reference category. Dummy variable do not suggest any ranking of the categories. So without loss of any generality, we can define 1 for female and 0 for male. So you can switch, but you're the one who's going to decide which one's going to be the reference category. All interpretation of the results is made in relation to the reference category. Most of the time, a categorical variable is defined by more than 2 categories. We can have 3 or 4. For instance, the mode of a transportation is used to commute may be described by three categories: public transportation, driving alone, and carpooling. So in this case, we have categories. We have K categories. In this case, we have three categories. How many dummy variables are we going to create in this case? We're going to create 2. So it's number of the categories. In this case, in this example, we have 3: public, driving alone, and carpooling. We have 3. The dummy variable is going to be K minus 1, which is 3 minus 1, which is 1. And the last category, maybe we can use it as a reference. So in this example, we can define 2 variables, as we said. We can call them D1, D2. And D1 is going to be for the public transportation, is going to take the value 1. 0 is going to be otherwise. For the second variable, D2, is going to be 1 for the driving alone, 0 otherwise. We will not create another value for the carpooling, because if the 2 variables takes 0, 0 values, is going to be the carpooling value, which is the reference category. We will be talking about this. We will be seeing this in an example. So there is no need to add a third dummy variable. Again, these variables will be added dummy variables. Adding the third one is going to create something called information redundancy. But number of dummy variables is number of the categories minus 1. This is what we have to know right now. We will be seeing all of these in an example. The last thing is what? Finally, is another common transformation technique of the categorical variable is called creating category scores. And this is most appropriate if the data are ordinal and have natural ordered categories. For instance, when you do surveys, customer satisfaction surveys, we use ordinal scales: very satisfied, very dissatisfied, somewhat dissatisfied, neutral, somewhat satisfied, and very satisfied. So this is to indicate the level of satisfaction. We know that the level of satisfaction is a categorical variable, and these categories have order, right? So in this case, we can change these values from categories or text. We can recode them numerically using numbers from 1 to 5, with 1 being very dissatisfied, 5 being very satisfied. When you transform these categories into numbers, so this variable is going to be treated as a numerical variable, especially in some analytical techniques. And there's no need, by the way, in this variable to create categorical variables, dummy variables. And there's no need to reduce number of categories. It doesn't work. There's no need to do this. What we do is just we changing these categories into numbers. Because in this case, we are assuming that they have an equal increments between the categories scores, between the very dissatisfied and somewhat dissatisfied. So we are assuming that the distances between these are almost the same, right? This is to have an effective transformation. So we talked about 3 approaches that we use when we transform categorical variables using dummy variables and category scores or category reductions. And we will be doing all of these in the next example.